to mention at the end here, we do want to leave open some time for questions. So please feel free to type those into the chat, and between Conrad and myself, we'll make sure to address those at the end or follow up with you with further questions. So first and foremost, let's see, make sure I can advance the slide. There we go. A little bit about the intro and background. So people are aware of what HPC is, probably high performance computing in the simulation world in particular. But it's still a hazy topic. So the main thing is, you can consider that, large companies, huge R&D departments make use of HPC, but is it right for me? But the time in which you're down and under the gun, and you've got your manager asking to get some results done, you're behind the deadlines, you're at the 11th hour trying to do something, and your manager asks you what you need to get it done. I think the obvious first answer would be cores, lots of cores. But besides everybody just wanting faster solves, what can it do for you? It's not just about making things faster. Yes, that's an example of where you're under the gun and trying to get it done quicker, but that does not make a good justification for onboarding and bringing on HPC. So you need to think a little bit further ahead of it. But thinking ahead of it is complicated. Parallel scalability is a complicated field. It's not always going to be linear. In fact, it's almost always not. So you can't always expect that you can just throw computational power at the problem and end up, infinitely multiplying your computational speed. So that perception has led to make it that it's high barrier to entry. It's kind of confusing. It's high maintenance. It's presumed that it's reserved for, again, those large companies that have big R&D divisions, or people who are driving simulation all day, every day, and are sitting there waiting on loading bars. So altogether, that has made it so that the whole result of this is an unclear ROI. It's hard to understand the parallel scalability. It's hard to understand the costs that are going to go into it, and most companies are hesitant to take the plunge. So, a few assertions that I intend to make throughout this presentation. Number one, I want to erode that concept that HPC has to be a giant leap. It does not. It is approachable. There are many small steps that can be taken towards that. There's many options that can be used to use it temporarily in small batches and eventually work your way up to large usage. So it's not just a singular large leap, as I'm sure people are aware in at least in vague terms that that's a possibility, but I intend to talk about that a little bit more here. I also want to assert that both the expenses and the time savings can be reasonably predicted. Time savings, obviously benchmarks and studies, things like that, definitively tell you how much faster it's going to be, but that's usually after the fact. So it precludes people jumping in because they want to make that sort of prediction ahead of time. Those time savings can be reasonably predicted, and the expenses those would have can be reasonably predicted. People are worried about hidden costs and things like that. I intend to kind of show you here how you can predict those costs. Another assertion is that the shift to HPC can change the way you do simulation, open up entirely new ways of thinking about it. It's not just a matter of running one test case as a stand-in for a physical experiment that you do. It is about bringing simulation in broadly across the design spectrum. The last assertion is that, yes, it can be approved by your management. Now, I obviously can't say this for sure without speaking with your management, but I can lay out a pretty compelling case for it. And we've obviously worked with lots of different companies in understanding if it does make sense for them and putting together a justification for so. Now, I intend to prove those assertions through about 4 major topics that I'll cover today. So the first is going to be just the concept of parallel scalability. We're going to start at a base level. We're going to talk about what sort of factors influence the speed and efficiency. Again, this is a very deep area, very deep topic, so I will stay pretty surface level in this, but hopefully it'll give you some intuition so you can apply that towards your use case. And then we can follow up with more specifics as it goes later. And then I will talk about the adapted methodologies. I was mentioning how it should be applied in many different ways. Once you have higher computational power and simulation becomes more ubiquitous in your design cycle, you can use it in many, many different areas. It really opens up a lot of doors. So we'll talk about how to use it there. Then we'll talk about the value of HPC solutions so you can predict it. Again, predicting your time savings, predicting your faster time to market, predicting things like that so that you can actually quantify that ROI to understand if it makes sense. And then it's not a matter of necessarily if it makes sense, but what part makes sense. So you can rent HPC by means of cloud or otherwise. You can rent the software licensing by means of AEC or otherwise, or you can invest to own those and bring those in-house. So we'll talk about the balance between cloud and on-prem type computational power. So starting out at the top here, let's cover some basic terminology and some basic understanding of what's happening with parallel scalability. So those who've worked with me or talked to me before know that I do like to use and abuse analogies, so I will be doing that here, so bear with me a little bit. I feel like it helps us to understand what is happening under the hood here. So let's first start off by saying we have a set of 60 questions. It could be an exam or otherwise, but we essentially have 60 product computations that need to be done. 6 times 4, 4 times 3, 3 times 8, whatever. We have 12 students to take it. So it's not necessary that each student needs to take all 60 questions. It's just that we need to get 60 questions done. So what is the way to get that done? Well, first we can pick one student at random to take the test. Obviously, we can assume we want to take the one who's fastest, but we don't know that for sure. So we can just take one at random. And let's assume that solve time for that student, those 60 questions, is a total of 4 minutes. That's 4 seconds per problem and about 15 problems per minute. Now, that's an average student, not necessarily the fastest, not necessarily the slowest, but let's say that that's representative of the average of what the students are. The other way we can do this, of course, is to do it in parallel. Now, we have 60 questions, 12 students. How handy. We have 5 questions each. So if we distributed those across those 5 students, let's say that the last student finishes their portion in 30 seconds. So the total time was 30 seconds. Now it's 6 seconds per problem as opposed to the 4 seconds, again, because we're dependent on the slowest. And that's 10 problems per minute per student, and we had 12 students. So we got the whole thing done in 30 seconds or 120 problems a minute. Pretty fairly straightforward, but let's do some calculations on that. Let's say in that serial one, once again, 4 seconds per problem and 15 problems a minute. In parallel, 6 seconds per problem, 120 problems a minute. The 4 seconds to the 6 seconds is load balancing. Now, in this example, in this analogy, you'll have to forgive for a moment. Students are slightly different in their speed. That's not necessarily true, but it would be true that problems are different in their time to be solved. 1 times 3 is clearly a lot easier to solve than 48 times 32. So problems need to be distributed according to the capabilities of the students, distributed fairly equally in order to reduce that. But in this case, we have about a 50% impact just due to load balancing from 4 seconds a problem to 6 seconds. But we do have a speed scaling from 15 problems a minute to 120. So let's do the math on that. Speed increase went from 120 minus 15 divided by 15. So that's a 700% increase in the problems per minute, right? Plus 700%. Compute power went up by adding 1100%. Now I didn't do these over, it's not, it isn't added, right? Plus 1100% instead of 1200% total, just because of the fact that you want to normalize this. So you do that with calculate your efficiency increase. You take your speed increase divided by compute power increase and 63% scalability, right? 100% would be that every time you double it, you get twice the speed. That doesn't generally happen in practice. And in this case, that time impact is solely due to not distributing the balance of the problems according to the speed of each student, so that you end up with an impact from 4 seconds per problem to 6 seconds per problem. Let's introduce a new concept. Let's say instead of each of these problems being able to be solved independently, they require the answers and communication between the students. So in those 60 questions, you anticipate this, you arrange them in a circle, the 12 students in a circle, and you once again distribute the same 5 questions. But let's say that the first question can be solved independently, but every question thereafter requires the answer to the previous question to be known. And that needs to be from the previous question from the student on your left. So every student needs to communicate the answer of their problem before they can start with the next problem. So take an example. Take that student right there. Say that the first question, 5 times 3, independent, can be solved. But the second question, 4 times x, where x is the solution to question 1 from the student on the left, right? So in that way, information would be, fed, counterclockwise in that case. Similarly, question 3 might be 2 times y, where y is a solution to question 2 from the student on the left, so on and so forth. Now we've introduced communication speed impacts. Not only do they have to solve the problem in an efficient, load-balanced way, but they need to communicate that. So let's see how that impacts our solution time. At the end of each round of questions, which is, again, about 6 seconds based on the slowest student, there begins a round of communication. Let's say this takes about 4 seconds. So now, instead of 6 seconds, it originally was 4 seconds per problem, but now it's, instead of that 6 seconds, it adds 4 more seconds. It's 10 seconds per problem. We have still the same 12 students solving them simultaneously, so 6 problems a minute times the 12 students, so we now have 72 problems a minute. We're going to do the math on here. Obviously, that we'll skip past that quick, but if we compare that to the same original run, which had 72 minus 15, so it had 15 problems per minute, that's an addition of 380% speed increase. Compute power is still the same, 12 versus 1, so that's added 1100%. So now our efficiency has dropped to 34.5%. This is accounting for both the load balancing and the communication aspects. So that is, in a nutshell, what is happening for most types of simulation. Now, obviously, I'm talking here broadly between the HFSS and CFX and Fluent and mechanical and LS-DYNA. There are many different things that go into this, but simply thinking of it in terms of this is the easiest way. Now, obviously, I've used and abused this metaphor. Should have been very obvious that in each of these cases, the simulation problem was the 60 questions that needed to be solved. The 12 compute cores were the students in the case, and the communication interconnect is the language, the method by which they've been communicating their answers. So now, obviously, this is CPU-based scaling. There are considerations for the amount of RAM, the disk read-write speeds, and so on and so forth. But we'll assume for now that in this case, the CPU cores were the long pole in the tent, the bottleneck, and everything else was able to keep up with the process. Again, not always true. Many things to consider there, but we'll assume in that case. So now that we've talked about that analogy at length, it kind of leads to some potentially intuitive conclusions. I think it's important to view it that way because now these things will make a lot more sense. So first of all, load balancing depends on accurately forecasting the workload for each task. Lucky for you, this is a very well-paved path. This is a field of study that a lot of people have put in a lot of work. And most of the time, let's say you're running Fluent, you don't have to know that it even happens. You do partitioning, you specify how many compute processes you have, and you don't have to consider exactly how it's weighting those partitions and how it's dividing up that work. It's pretty efficient with how it does it. Now, if you're wanting to, Fluent does have quite a lot of information in its parallel tab that can show you all this load balancing and such, but you don't have to. Most of the time that is pretty well laid out. But sometimes you might not know how much workload is going to be distributed to each task because maybe you have mesh adaptation enabled. So the partition that started out with 40,000 nodes grew to 4 million, but its neighbor node is still sitting at 40,000, or its neighbor partition is now sitting at 40,000 nodes. Obviously, that would be an inefficient load balancing, and you need to recompute that. But again, special consideration. But the intuitive conclusion here should be that you need to kind of balance that in order to make sure your scalability is up to the task. Second, different HPC workloads will have different communication requirements. Some need to constantly talk to each other, some don't. Keeping with the analogy of Fluent here for a minute, and I'll talk about mechanical in a second, but keeping with the analogy of Fluent, if you're solving a large wide open domain and you partition it into 120 different partitions for 120 cores of a compute, there are physical boundaries drawn in your model. There are individual zones that are attributed to each cell. Now, the boundaries that pass information from one core to the next need to communicate. They need to tell each other what the velocity and pressure and temperature and density and such is passed across that boundary, either with upwind differencing or central differencing or whichever. that's a communication requirement. But if you instead have a very long, skinny duct and the actual boundaries between those partitions is very small, then most of your computations can be done within a core and not needing to transfer to others. So huge differences in those types of scenarios. Mechanical, as an example, I promise. If you have a lot of bodies in your model, each of those bodies might be assigned to a different core, and they don't necessarily need to communicate with each other beyond just the contact patches that send that information. So very different scenarios in each of those, and obviously that depends on how well your model will scale. The more parallel tasks, the higher the communication bandwidth required. That's probably potentially intuitive as well. A lot more talk needs to happen if there's 400 people in a room versus 5. And there are diminishing returns as the core counts continue to increase. Those impacts, those percentages of lost efficiency add up as you scale further and further up. So you do have diminishing core returns as core counts increase. But the larger the problem, the stronger the parallelization benefits. There might be some, using our analogy, it might be found that 4 questions per student is about the ideal place to be. So if instead of 60 questions, you have 120 questions, well, you can double the number of students from 12 to 24 without having an impact in efficiency. But beyond that, you do start to get some. Obviously, if you had 60 questions, does it make sense to use 120 students to do it? Probably not. So let's look at a graph like this. Now, this is an example of a benchmark graph. I want to say it's theoretical in this case. We've done many benchmarks, and we've collated a lot of data. And between that, we can fit through these logarithmic curves that generally fit pretty well to data. Now, it's going to be, again, dependent on the model and the simulation type, the physics you're solving, so on and so forth. But let's just say for now that this is an example benchmark that you run. You can look at it. It's aligned by different mesh sizes. So the bottom mesh size being 2 million nodes, 15 million nodes, 40 million, and 100 million nodes for otherwise the same problems that should be solved. So keeping the prior conclusions in mind, we can now understand this graph a little bit better. First, the relative speed up is generally sublinear. Now that means that if this is you multiply your core count by 10, do you get 10 times the speed up? Probably not. Probably sublinear than that. Below that. There are times where that goes superlinear. I'll pause for a minute and mention that, but generally speaking, that's based on, it's a fraction benefit or a multiplier based on the initial 4-core run, 8-core run, 10-core, however many is your smallest one. And that can influence and cause potential, scaling problems if, for instance, it overloads the amount of memory or the cache per the core and things like that, that can make it so that anything beyond that becomes superlinear. But generally speaking, it's sublinear. Second here, the larger the mesh count, the further along the scaling goes before, quote, falling off. So as you can see here, the lightest blue, the 100 million nodes, gets quite far up here, about 400 cores before you start noticing those sublinear effects, whereas the 2 million node falls off almost immediately. And in fact, has an inflection point, curves down, and ends up at some point negatively affecting the speed, where actually the more you go up in core count, the slower your run is. And that can be just because your communication requirements become too large and your interconnect can't handle that. So looking at benchmarks that all basically have a similar trend to this. Now, some are going to change this. Instead of relative speed up, they're going to be maybe just hours and minutes. Others are going to use some compute power metric and such, but essentially they're going to look similar to this. And this is what you want to see when you're understanding whether to invest in HPC. So it's reasonably possible to predict the curve of this and the shape of these plots ahead of time, which is very, very valuable. So the primary variables that affect the curvature, as we said, the model size, typically the mesh nodes. We talked about that at length. But the interconnect speed, this is the communication bandwidth that happens between the cores on a chip, along the memory lanes on a board, and on InfiniBand or interconnect or fabric between compute nodes. So got to make sure those are up to par to be able to handle that communication. CPU architecture itself, I talked about the cache and the lanes of that. Similarly, it affects communication speed. So that affects, the curvature, how far this goes before it falls off. And lastly, the memory bandwidth, again, the communication, the information that needs to be stored and communicated across those cores. Those last three are primarily hardware based. The top one is primarily model based. Again, there are a million other things here. I'm just kind of keeping it simple here. But the other thing I want to mention here is if you have no idea where to start and you're trying to calculate about how much faster it's going to be, you don't have to run a benchmark to get any idea. You can start off with some sort of quick estimations. It's actually quite reasonable to start with 50%, 50 to 95% based on your model, and run a scalability test, a theoretical test, to understand how much time savings that's going to be. Now, that's usually quite useful in and of itself because you can predict before you start your simulation about how quick it's going to be. Reasonably, we can do this, especially with Fluent Dyna. HPSS to some point, although that works a little bit differently, but you can do some of these predictions ahead of time and be reasonably accurate. All right, on to the second section here. This is talking about how you adapt your methodologies to shift how you use simulation when you have HPC. So I'll keep cruising along here. First of all, an engineer empowered with a couple hundred cores at his fingertips is generally more willing to fail than somebody who's only got 4. Running it and knowing that you only lost 15 minutes because you tried something that didn't work is a whole lot better than saying you ran it for 72 hours and it failed. Learning requires failing. So fail faster and fail often. I want to stress that point. It's very, very important that the most capable and innovative design engineers are encouraged to try things that are going to fail. Instead of just finding out as a checkpoint at the end that you just ran an experiment and it passed, you found out all the ways it doesn't work, and you know all the stay out zones, and you know all the parameters that affect that stay out zone. So using this as an example, it looks like it's a tool holder here with a design of experiment study, a response surface all built out for this tool holder to show it what variables are going to cause it to fail, or variable combinations of multiple variables are going to cause it to fail and which ones are going to cause it to pass. It's a lot more powerful to know that information than it is to just know, well, this one design worked. Don't treat it necessarily as a stand-in for experiments or validation. Treat it as a tool for exploring. It really does change the paradigm when you think that way. Generally speaking, I'll go into this. I know most people here are engineers and probably don't need this to be explained to them, but it helps set the stage. The design is a process of starting broad and narrowing your focus, right? You start out with vague ideas, larger than a bread box, smaller than a Chevrolet, and you start to understand as you go a little bit more refinement and understand how it's going to work. So in this new analogy that I'm going to use and abuse, you start out with this foggy idea of what your object is. You can consider this as you're shooting at a target. Maybe one of them hit, but a whole lot of them missed. But that's good. You learned from that. You understood, you want to calibrate to that one that hit. You want to kind of avoid the parameters that you used or the angles and velocities that you used that missed here, right? So as you start to mature and you use simulation here and start to mature in your understanding, you move into the refinement phase. Now it's starting to come a little bit more into focus. You've hit the target generally. Maybe you didn't bullseye each time, but you hit the target pretty generally, and you're starting to understand your model a little bit. And then finally, by the time you do run to your validation studies, your stand-in for experiment, if you will, you're bullseyeing the target, and you know you're bullseyeing the target. And so you have a well-designed, robust model here. All right. In order to do this, though, one of the big shifts in perception here, or shifts in mentality, is instead of running one design, you run a parametric study. Generally, you can say, let's say you have a large building with a ventilation system on the roof, and you have exhaust 30 feet away from it at a different angle. You need to understand not just, will I re-ingest some of that exhaust into my ventilation system, but at what wind angle, velocity conditions will I? What other parameters are at play here? I need to design a baffle for it. Well, will that, what shapes of baffle is going to be best, not just design one and test to see if it works. So opening up parametric modeling changes things a lot. So referring back to my original analogy here, what if instead of one big 60 question exam, you had 6 separate 10 question exams, right? Still with the same intercommunication requirements, right? They might need to talk to each other about how to solve the problems, but only within that problem set. So the solutions to the first exam don't influence the second, third, fourth, or fifth, or whatever. But do you run them in serial? And you have the same 12 students, you give 10 questions to them 6 times in a row? Or do you split up the exams? Let's say you have 6 teachers in this case, and give a 10 question exam to a pair of students and do those all simultaneously. Now, I'll leave it as an exercise to you. Given what I assumed in the first test, we can actually calculate the parallel scalability of each of these cases, but I'll leave that as an exercise to you. Suffice it to say, the bottom answer is probably likely to be the one that is going to solve the total case faster. Same workload, same 60 questions, arranged in 2 different ways, give you 2 vastly different times to complete. So when you open that up and you're looking at those parametrics, same way that HPC enables faster runs, faster singular runs, it also allows more runs through parallel solves, and those aren't always the same thing. So parametrics, as I talked about, is a great example of where it can be used. But then you can build full design of experiments. It's not enough to just know, will it work at this? You can say which parameter combinations, which design configurations will work and which ones won't. And then eventually you can build a response surface on that and to run an optimization study. I'm a big proponent of optimization for simulation. Once you've gotten under your belt the proficiency in driving simulation, that feels like a level up. It really feels like you're entering into a new field beyond that. And it's very, very, very powerful. You can run sensitivity studies in that optimization. Generally, after you've run a response surface, you can look at and understand sensitivity studies on different parameters. So one of our main tools for doing this, there is actually Design Explorer, which is built into Workbench that can be used for this. But OptiSlang is a very, very, very powerful tool for doing all of this. Design experiments, optimization, sensitivity studies. It's very, very robust, can be used with a lot of different tools that can be integrated with it as well. Yeah, come talk to us if you want to get into this. There's a very, very deep field here in Ansys OptiSlang. And as I talked about, all of those prior discussions about how scalability works come into play here and dictate the optimum use of resources. So many times I would run a case where I would need to run design of experiments of 100 different cases. I would start to run tests on those cases ahead of time to understand where the sweet spot is, where the highest parallel scalability was, whether it was at 30 cores, 40 cores, 50 cores, 60 cores, and then I would parallelize my runs so that I would do as many as possible within a short amount of time. So that's kind of a fun and powerful exercise to do. But now we'll talk about the value of HPC solutions. And so I talked about how you can kind of think about parallel scalability, how you adapt your methodologies to cover it. So let's try to compute out what the value of that is going to be, the return on the investment. So typically, without access to HPC, simulation engineers can spend upwards of 40% of their time, I like to say, watching loading bars. That usually comes as a shocker to management, but I can tell you, simulation engineers, I'm sure several of them here are nodding their heads. We do spend a lot of time watching those loading bars. Nobody likes that. But we have to try and convert that into cost, right? What is that going to save us? So let's assume a modest internal billing rate of $150 an hour. Now, this is, to cover all of anybody who's worked in project management understands how you do these. That's a pretty modest number. I've seen more than double that, obviously. But generally, this covers your simulation engineers, your salary, your benefits, your overhead, the software, the lights, the building, the rent, the computers, the electricity, other admin, things like that. So by the time all of that's considered, you assume an internal rate of, let's say, $150 an hour, which is pretty modest again. Let's say a utilization rate of 75% on that engineer. If you're saving that 40% of their billable time saved, that's $100,000 per engineer per year that is saved by investing in HPC. Now, big caveat, this of course assumes the engineer is fully focused on simulation work. Not all are, many are working many tasks, but obviously you can do some fractional equivalents of that to calculate. But it's that can add up pretty quick. That's the primary way that people think of it. The second way is fidelity increase. Should be maybe potentially obvious after I've talked about it at the beginning here, but often the lack of computational power impacts the model size. Time is, after all, proportional to fidelity and inversely proportional to speed. Generally, people think of increasing the speed as reducing the time, but it's just as true that generally time is the practical setting. You have a deadline, you have a project completion date that you are trying to shoot for. Engineers generally adjust the fidelity of their models in order to meet the deadline. That's a constant truth. So when you increase your speed, you generally increase your fidelity. It doesn't just reduce time, it boosts your fidelity. That fidelity can have significant financial ramifications that can be quantified as well. Again, this is something we do with customers all the time when we run these tests out to see where we understand their metrics. But inaccurate results can lead to product failures in prototyping. Oftentimes we have customers who report to us that every time they go and run a prototype on the bench, it costs them $5,000, $10,000, $15,000, $20,000 if they're a small thing. Sometimes it's much larger than that, and that can be weeks or more. And every single time they have to come back to that well, that's very costly. And that's if the problem is caught in prototyping. If it's not, and it goes out to production, that has much bigger ramifications. There can be legal ramifications. It can have recalls. You can have poor reviews. It loses your competitive advantage, etc. So those can be costly and can be quantified. In the flip side, it leads to increased innovation to have a higher fidelity. So you can enter into new markets. You can run types of simulations that you never could before. You can solve problems that nobody else is in your field or none of your competitors are able to solve, giving you advantages and a shorter time to market. So you can obviously get that done faster. So you can certainly quantify those types of things to understand, just if A times B times C is less than D, the cost of implementation of HPC, it would be a cost savings. Lastly, and this is just more general, the increased simulation throughput enabled by HPC really makes it, again, more broadly employed across the design phase. But the intangible part here is that it really makes your engineers generally more powerful. So first of all, you can run a bunch of what-if scenarios during the ideation phase. Instead of just going with your first gut instinct, you can test a lot of things so that by the time you are pointed in a direction and running, you're at least reasonably certain that you're heading towards the target. Sets the whole process in motion with a lot more efficiency. The parametric exploration instead of the single point validation, again, this is the refinement phase right in the middle, so you can do a lot more of those parametric analyses. Just in general, more ubiquitous simulation across the design cycle. And this is the one I think is quite important as well. Reactionary question and answer simulations when problems arise. Let's say you have designed a full enclosure and a bracket mounting system for a electronics enclosure, and somebody comes to you and says, the electronics department just told us we need to put in a sensor here. We need to drill a hole right through where your bracket is. Is there still enough meat in that bracket to have a structurally sound mounting system? You're pretty late in the game, and somebody needs a decision now. They're already out there, cutting chips or producing this. You need to be able to get an answer. With an HPC, this happens all the time. People come to you and just say, hey, can you just run this for me? If your answer is, well, give me 72 hours and I'll get you an answer, it's not quite good enough. Generally speaking, that's something that with HPC you can get done in a couple hours and get them an answer so that they can proceed with production. All right. At the end of the day, this results in a more powered design engineering team. They're just generally able to answer more questions and do a lot more. It honestly bolsters their capabilities and their expertise as engineers, which is a very valuable thing for companies. It makes it so that you're making data-driven design decisions. You aren't just guessing, frankly. You can check everything. You have the power to go and check things. It does deliver competitive advantages over rival companies, as I mentioned, things that they couldn't do, you can do. And it reduces your prototyping costs, which again, as I said, is an easily quantifiable thing if you're trying to figure out whether HPC is necessary. So the last of the four topics here, and this is a big one, is probably the one that a lot of people have questions about. So I want to make sure to provide a lot of time to cover this topic, but this is rent versus own versus both. So evaluating the balance between cloud and on-prem. All right, again, I'm going to use another analogy, but let's talk about driving to work, the vehicles you drive to work and such. So let's say in your current situation, you drive to work every day. I don't, I work from home, but let's assume that you drive to work every day. But every once in a while, you have an infrequent need to transport larger items that don't fit in your car between two of your office locations. Say it's once a month or a couple times a month or something like that. Do you, one, rent the car you drive to work in, and maybe a large van, or and do you rent that car that you drive to work in? Probably not. And do you wait to transport any of those items and therefore stall your business and hold off until you feel that you have enough transport needs to justify purchasing and operating a shipper van? Clearly, you don't do that either. More likely, you purchase the car that you drive to work in every day, or maybe lease it, but purchase or lease, and you rent that transport vehicle when you need it until you get to the point that you can justify owning that shipper van. So, based on that, does it make sense to own or rent computational hardware? I would venture the answer is yes. It makes sense to do both. Don't treat those as competitive. Almost everybody we ever talk to always thinks of those as two completely different things. They have to make a decision when they start simulation. Do we do it in the cloud or do we do it local? I think that's the wrong way of viewing it. I think the answer is almost always both. So let's say that this is your annual computational needs divided by week. And this is the highest. I'm not going to talk about per hour here. We'll talk about that in a minute. But let's say that this is the highest core count that was consumed in that week. Assuming you had all you can eat unlimited. Now, most people don't, and they can't test this until they get there, but we'll get there in a minute. But assuming you had unlimited, this is what your actual needs are. Obviously, you can see spikes in there where you need 256 cores, but a lot of the times you're sub 100. So it's often beneficial for you to consider this 80% rule, which is you own 80% of your capacity and you rent anything that's bursts above that. I call that burst capacity. As simulation or as cloud becomes more affordable, which actually it is getting very, very affordable lately, this might become 70%, 60% or lower, but it's unlikely to be 100% for many reasons. So consider it this way, and you just deciding where the break-even point is. So both licensing for the software and the hardware has similar rent and own options. So you don't have to think of those independently. You can think of those independently. You can think of each individually. You don't have to think one is a barrier or the other. So I sorted the computational needs here just to make it easier to understand rather than being a jagged plot. I just sorted them by their week or by the usage in that week. And we can consider that those top times which it went up to 256 cores where you had really big models, we rent, and the bottom you would own, and there'd be no limitations on owning, but the rent would be a hourly, generally, pay as you go. So for the software side of things, obviously you can lease and buy and own paid up software, or you can rent the software, which comes in the form of Ansys Elastic Credits or AECs. On the hardware side, it's cloud versus on-prem. I think people are pretty aware of that difference. So this model, this rent model, provides a pathway to demonstrating the value of HPC and understanding when to invest before you invest. I think that's an important consideration as well, that generally speaking, rent is the entry model, and you can start to understand how often you use it, at which point it might make sense to own it. But obviously you couldn't generate, I'll go back a slide to show, you couldn't generate this graph until you had enough capacity to test it. So moving to the next slide here. So let's run some numbers, and these are real numbers based on costs for this exact application. So if you have a 256 cores, now I'm going to bring in the hourly because per week I'm not assuming that that 256 cores is 24/7 through that whole week. I assume that it's about 5% utilization, which is I think roughly 8 to 10 hours in that week. So with that sort of infrequent usage, 8 to 10 hours here and there throughout the year, that totaled about $1,000 to $2,000 a year in rental costs for that. Now, to own that capacity, 256 cores, you're looking at six figures. I don't know exactly the cost on that. You can go check at different hardware providers, but to get 256 cores, you'd be looking at least 100,000, probably more. So the opposite, though, the 32 to 96 cores that's used throughout here, let's say that has 65% utilization. And I did scale it, 65% of 32, 65% of 64, 65% of 96, so on. That would total, if you were to rent it, about $25,000 a year. But to own that would probably only cost you about $20,000 a year, right? So in each of these categories, the left one, the 256 cores, probably doesn't make sense to own. You're not going to forego $1,000 to $2,000 a year by spending $100,000. But on the right, you would. You might forego $25,000 a year by spending $20,000. That'd be a smart financial decision. So this is clearly heavily dependent on the usage scenarios. And as I said, you can generally start to obtain those by going into a rental option first. But generally, I would say it's important to make sure you have both. As a point here, BrandSim we have great partnerships with leading providers of both options here, as I said. So if you're looking to get hardware for yourself, whether that be desktop workstations or computational clusters, we do have a great partner in Exact. We have custom machines that are tailored for Ansys simulations that we can help you configure and understand. On the other side, on the cloud side, though, we have a fantastic partner with Corvid HPC, and they are a cloud-based. Well, it's a singular on-prem, single location, but it's obviously accessible to users via cloud, specifically built for simulation, and they have specifically built workflows for Ansys as well. So we help customers in showcasing that all the time. So I'll wrap up this section by returning to the assertions that I made at the top of the hour. So first, I hope I proved that HPC doesn't have to be a giant leap by showing that there are rent options, there's cloud options that are available until you are ready to purchase, and there's a clear understanding of when it makes sense to do each. Both the expenses and the time savings can be reasonably predicted. I hope I showed at least a baseline of how parallel scalability works with some overall predictions. There are, again, infinite ways that you can run benchmark studies and find this out, and I'm happy to provide more of those informations or help with benchmark study. But you can at first, right out of the gate, reasonably predict it with some certain percentages. So they follow predictable trends, you can predict it, and the cloud and licensing costs are calculatable based on that simulation time. We do have calculators that can run all these types of calculations for you as well. Happy to run those if you have information about your models. I asserted that the shift to HPC can open up entirely new ways of thinking about simulation. Hopefully I've talked to you a lot about how engineers with HPC are more willing to fail. They can employ it more readily throughout the design process and explore many other ways of running simulation, including parametrics, optimization, sensitivity studies, etc. I did assert that it can be approved by your management. I can't make that call entirely by myself, but I can, of course, show you that there is clearer paths to ROI justification that most people are generally not comfortable making, and hopefully I've shown you by the end of this presentation that you can put that together and make a justification for it. And then, like I said, we help customers with this all the time, so we can help you understand when it makes sense. And that's going to wrap up the content portion here. So I am going to open up for questions. Looks like I've got about 13 minutes here until the top of the hour, and happy to answer any questions. So I guess I'm looking at the chat. I don't see any that are posted there, but please feel free now, if you have any, to type them into the chat.
Yeah, and just thanks, Adam, and thanks everybody for attending here. Like Adam just said, if you have any questions, feel free to put them into the chat. We do have one here that just came in from Vincata. They're asking a question about GPU versus HPC. Ansys seems to be promoting usage of GPUs for increased performance with significantly lower costs. What are the benefits of sticking with HPCs, or is it more a combinational approach, GPUs and HPCs, that is required?
Yeah, no, that's a fantastic question. You're absolutely right to say that GPU is a great new entrance into the HPC world, and I could again talk an entire talk on that. if you're curious about it, on the Fluent side of things, we did a great webinar with Alex Lefebvre on our team recently, who covered GPU-based solutions in Fluent, and that is one of the ones that's most kind of disruptive in the HPC world. Other tools are Rocky, is a fantastically scalable native GPU solver. The couple things to pay attention to is, I just use that word native solver. Whether the tool itself is natively running the calculations on the GPU or whether it's using the GPU as an accelerator. Generally, if it's used as an accelerator, the gains are fairly modest. They're nowhere near the same potency that you would notice with something that is native. And that's what is different, is the Fluent is now a native, or has now a native GPU solver, and Rocky is generally native GPU. Generally, the benefits of those are they are significantly cheaper to get the same computational power than it would be to get it with CPUs. A couple examples are Fluent, for instance. You can buy, say, an $8,000 to $10,000 GPU that would replace about $70,000 to $80,000. I'm making broad estimates here. About $8,000 to $10,000 GPU can replace about $70,000 to $80,000 worth of CPU equivalent hardware to solve that same problem. That'd be about the potency you'd get. So definitely a big impact here. We also have through Exact. That's actually a fantastic partnership we have with them. They have a lot of options for NVIDIA-based GPU computational powerhouses, so we can work with them.
All right, we have another one here from Matt. How does the rent buy question change when you have ITAR or other controlled data requirements?
That's very good. So a lot of general purpose cloud providers will have a separate ITAR type infrastructure. I mentioned Corvid here. Corvid is entirely ITAR compatible. So you need to make sure of that, because if not, that data might be housed in many different areas. Some of those areas might be overseas, of course, and that would break ITAR. You can't do that. So when you make sure you ask for an ITAR specific infrastructure, you're making sure that all the hardware is on domestic soil, of course, and has all the equivalent restrictions for that data handling to make sure that it's never out of the U.S. person's hands. So Corvid, like I said, is fully ITAR compliant. That's where we direct our customers pretty much every time we have that. They have secure transfer, FTP, and transfer mechanisms to handle all of the processes from your machine to it, and they stay entirely housed within ITAR protocol. So very, very good question, and it is definitely something you need to make sure you're aware of when you engage with a cloud partner.
All right, we have one from Greg here. What are some of the hidden costs to look out for when you're getting started with HPC?
Yeah. I'm presuming, well, I'll answer it both ways, I guess, on-prem versus cloud. So on-prem is the easier one. Obviously, that initial investment is not all of it. You bought this shiny new, $150,000 cluster, and you brought it in-house. You have to keep it running. You have to keep it cool. You have to keep, if memory can go out every once in a while, you need to keep replacing those, and you might annualize the cost of the whole cluster over an 8 to 10 year cycle or something like that. So those costs are very important. Obviously, you need to employ generally somebody to maintain it. That might be, it's sharing some of an IT burden with somebody else who's IT focused in your company. It might take a decent amount of chunk of their time. So that is certainly something to consider. Electricity and cooling and HVAC and stuff like that for whatever room you place it in. Those are significant, but not huge. And so you think of those costs, of course. On the cloud side, which is probably what the source of the question was, there's data storage and transfer fees depending on your provider. And there's, generally speaking, it's per core hour. I actually should have mentioned that explicitly. That's how the calculations I came up with in that those slides were based off of, but they're generally per CPU core hour of compute. However, that you need to keep a local client running. If you're running it and doing your prep and post processing, you'll run it on that machine as well. And some providers charge transfer fees that can add up, AWS, Azure, and things like that. I've seen those certainly. Corvid, they're really nice. They do have data storage costs, but they're very manageable. And it's pretty upfront. You have a single data storage cost. You have a single implementation cost that comes up front. And then after that, you're just paying on the core hour. And I think it's $10 per terabyte per month or something like that. And so that stuff's pretty predictable up front. But if you're going with some other provider, certainly make sure you look at all of those other transfer and storage fees and things like that that might add up.
All right, looks like we have another one from Samantha here. What's the best way to try out HPC on the cloud and understand whether it would work on our model or not?
Sure. This, again, something happens all the time. So I alluded to the fact that not all models scale the same. In fact, they almost generally don't. You can predict those ahead of time, but often, the proof is in the pudding and you like to see it tried. So our partnership with Corvid is really solid, and we do, occasionally go through and run benchmark studies to test it. We can also make sure you can get access to test it yourself so that you can understand the workflow and understand how data transfer occurs and things like that. We do have those trials. It's just a matter of come work with us and we can make sure you can try it out. Generally speaking, also not just is this, give you the warm and fuzzy so you understand how it works, but it provides real metrics that you can then base a decision on.
We have one from Faisal here. If we have both on-prem solving capabilities and cloud options, how much of a burden is it to transfer files back and forth?
Yes. So I'll take as an example, you are setting up a geometry, then you're meshing it, then you're running it, and then you're looking at the results. The file sizes definitely change all throughout that process. Geometry files are very small. Those are going to be almost instantaneous transfer speeds generally. Large assembly models, notwithstanding, but generally those are small. Then the mesh size increases the file size, and then the simulation increases that file size even more. Good use of cloud-based is to make sure you do the prep work ahead of time with the geometry and setting up the mesh settings. And then transfer your file and then run the meshing and the solution out on the computational or on the cluster side, and then bringing the results back when you're done with it. You can think of the fact that you can remote into those sessions. Generally, you use what's called like a remote desktop at the cloud side, at the cluster side. So you're still capable of driving things. If you didn't anticipate that and you ran the entire prep on your local machine and then transfer it, those transfer times can add up and be kind of prohibitive. But if you do that ahead of time, it's actually pretty straightforward. I remember when I started, it would have been pretty much a no-go to try it, but that was 15 years ago, and computational speeds or transfer speeds have gone way up, of course. So now it barely feels like a burden at all.
It looks like we have a two-part question from Matt here. How can you determine the number of cores per memory channel when choosing a new workstation, i.e. 4-channel workstation use 16 cores, 8-channel maybe 32 or 64 cores, 96 cores or 4 memory channels may not be worth the cost for either. And then he's got another piece here. This is for Ansys Mechanical specifically, and assume the model is large enough to scale with more cores.
Okay. No, glad you mentioned the mechanical part. I was going to answer kind of in general about all the tools, because that is something that differs a lot. I'll diverge for a minute. Fluent uses generally a lot less memory per solve and uses more CPUs. Mechanical can use a little bit more memory, and HFSS uses generally the most. But to your topic in particular, there is a good rule of thumb that I've carried along for quite a while that says that you generally want about 8 gigabytes per CPU core for mechanical. Now that is, again, big grain of salt. It's a rule of thumb. It's general. The more context, the more degrees of freedom, more bodies you have in your model, that number can go up from there. But it's obviously memory is how much of a problem or how big the problem you can house, and CPU is how quickly you can get it done. So that rule of thumb is just based on the fact that you don't make something that you reasonably can house in your memory, but it's going to take you 20 days to solve. So obviously that's the ideal. To find the optimum would be pretty model dependent, and again, it would be based on how many bodies, how many contacts, how much degrees of freedom, things like that are really going to factor into it. But 4, 6 to 8 gigs per core is probably where you want to live. 8 gigs being, kind of where you want to, the high end. So that's where you'd want to spec out a machine for that.
All right, that looks like it wraps up all the questions here. And again, thanks everybody. If you do have any questions, don't be hesitant to reach out to us on our website. You can just fill out a quick form or contact if you have a contact with one of our account managers or engineers. They'll gladly assist you here. But thanks, Adam, and everyone again for joining us. And I hope you have a great rest of your day.
Yeah, thank you, everyone. Appreciate it.